My fascination with quantum mechanics, I think, really started when I was a high school student taking chemistry classes. I felt that to really understand it fundamentally, I realized that I needed to study physics and that I also wanted to understand really kind of the mathematical underpinnings of this seemingly elegant theory that was necessary to describe, important topics like chemistry. And so in college, I found myself studying math, physics, chemistry, and at some point I sort of found the intersection of these interests to lie in quantum mechanics, where there's an elegant theoretical description, but also the capability to do experiments in the lab where we can directly probe phenomena such as quantum uncertainty. My name is Monika Schleier-Smith, and I am an experimental physicist. The key transformative idea that the field of quantum information science seeks to exploit is that information does not need to be encoded in individual bits, locally in individual particles, but information actually can be non-local. And that means that it can be stored in correlations between different particles in a phenomenon that is known as entanglement. The simplest quantum system is a quantum bit, which, like a classical bit, can be in the 0 state or the 1 state. The remarkable thing about a quantum bit is that it doesn't need to be in just the 0 state or the 1 state. It can be in what's called a superposition of the two. Fundamentally, it's unknown and unknowable whether the qubit is in the 0 state or the 1 state until a measurement is performed. And when the measurement is performed, it's almost like it has to decide. So I like to use kind of the analogy of a coin, right? A coin is a system with 2 states, heads and tails. And the superposition is a little bit like a coin that's floating in midair and it hasn't decided whether it's going to land heads or tail. So now the really neat thing, though, is that in a quantum system, you can have a phenomenon that's equivalent to me tossing a coin and you tossing a coin, and we repeat this experiment 100 times. And every time I get heads, you get heads. And every time I get tails, you get tails. But if I look at my tosses alone, the outcome always looks flat random. So there's this randomness, but there are correlations in the randomness. And that tells us that there's some information that I don't have. My coin toss looks random. You don't have it. But when we compare notes, there's actually some information there and not just randomness. So this idea of having information that's encoded in correlations, this is known as entanglement. And this is really the key resource for quantum technologies. We're currently working on advancing tools for controlling the interactions between laser-cooled atoms with an eye towards applications ranging from ever better sensors and clocks to new paradigms for computation to fundamentally secure methods of transmitting information over long distances. So we actually do experiments where we have a high degree of control over atoms that we essentially bring to ultra-low temperatures and pin in optical traps. And we allow these atoms to sort of talk to each other in a way that uses our ability to control them with light. So for example, we have ways that one atom can talk to another atom by sending a photon from one to another. This allows us to have information that is very rapidly transmitted over what on quantum scales is a very long distance. Broadly, the field of quantum information science is about exploiting this phenomenon for those technological aims.